Welcome everyone to the 2023 Vision Spectra Conference. Thank you all so much for joining us, and in this session, you will hear from Ruben Weintraub, the founder and CTO of Gidel. Ruben has more than 35 years of experience with algorithm development, which utilizes FPGAs, and he is joining us today to discuss improved raster processing while lowering power consumption. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. If you have any technical issues throughout this event, please log out and back in to rejoin the session. Ruben, we appreciate you for taking the time to present at the 2023 Vision Spectra Conference.
Hi, everyone. My name is Ruben Weintraub. I'm the founder and CTO of Gidel, and I would talk about ability to get over a gigapixels per second processing and still keep power reasonable. The agenda would be a little about Gidel, and then the strength of the FPGAs and why they're able to do these tasks, and then basics of FPGA processing, how you're processing. It's different than processing in the software. There's challenges of using the FPGAs, what they are and why. And today there's a growing need to use FPGAs. And of course, due to that, we expect FPGAs to be more and more used. And that's why we have the session today, as well as other sessions of Rising FPGAs. And finally, methods to be able to overcome the challenges, and this way enabling easier way of using the FPGAs. At the end, we would be able to show a demo representing some of these methods to overcome the challenges. Gidel is a 30 years technology leader with FPGA acceleration. We are expert in imaging and vision algorithms, specifically for FPGAs, and of course other things, but this is something that is uniquely for Gidel. From our products, we are having all kind of frame grabbers from either off the shelf or open FPGA that enables customers to add their image processing, their vision algorithms, and so on. We do have some image library in the FPGAs. Our platforms can run from a simple off-the-shelf grabber up to 800 gigabit per second in a single board, and also ability to have 300 gigabyte per second access to DRAM. On the other hand, we have the ability to have edge computers, and this is a picture of an edge computer enabled to run with CoExpress 12 and Jetson computer. We have so for the 10G and the Camelink as well. Finally, in order to be able to be successful with accelerating with FPGAs, you need tools and IPs to organize that. We are 25 years of developing those tools to be able to maximize the performance, which is really critical. And on top of that, to be able to simplify the design and speed up the productivity. And as a conclusion, also increase the system reliability when you're using the FPGA processing. When we're looking, what are the processing requirements in general? So in general, it's important to know that you have the processing capability. However, if you have only processing capability, you cannot do a lot, because you need also to be able to get the data in and out. You need to be able to access the memory for longer storage. And of course, you need to have IOs getting in and out, such as the frame grabber data and sending data to the next step. What is the FPGA resources that makes them unique? So it is a sea of lookup tables and DSP blocks. These things enables really to run in parallel all your lines of code. And since all of your lines of code are running in parallel, from that you get acceleration. The die-kit routing enables us to move data from one variable to another variable just by a wire. So it's virtually zero delay and zero resources and zero power. The registers that are used are mainly used for pipelining to enable faster clock rate and not needed to store, in many cases, information. Although some of the registers will be used, of course, for storing information like CPU registers. Then we have inside the FPGA a lot of dual port RAMs. These RAM have tens of terabytes per second, meaning that you can run very, very fast bandwidth to the DRAM and use that for line delays, for lookup tables, for small FIFOs, and so on. The direct I/O connectivity also enables the virtually zero latency and zero power or minimal power. So that's really advantages. Therefore, to take on top of all of this, in the FPGA, unlike regular CPU, you use what you need to use, meaning if you have a 10-bit pixel, you will use a 10-bit adders, 10-bit muxes, and all the logic would be at 10 bits. And if you're doing binary morphologic, then you need only 1 bit per data. To understand this capability compared to computers, about 10 years ago, there was experiment to run bioinformatics on about 400 FPGAs in our boards in 3 cabinets doing algorithm of bioinformatics. And it was with the same capacity or productivity as the largest supercomputing at that time. So the less bits you have per data, that means the FPGAs can excel better. That means a 64 floating point would not be good, but in imaging and vision, many things can be really accelerated using this technology. Something that is very important to understand is the way that you develop algorithms in FPGAs is totally different than the way you're developing algorithms in software. This is an example for a 3x3 filters. In the middle, there's the current pixel that we want to make the filter for. So in software, normally you would stand on that pixel, and then you would read randomly the 9 pixels from the memory, do the multiplications, do the summation, and then move to the next pixel. In the FPGA, in order to complete this part, we have 1 input and 1 output. From the input, and everything is running in parallel, so in 1 clock, we would have the full results of the full 3x3 filter. In order to do that, we need to have 3 lines. So the input comes into a line delay, And this over here is line Y. If that's line Y, this is the previous line, Y minus 1. And another line delay is the line before that, Y number 2. So in this way, we got 1 pixel in, and we already have 3 pixels from 3 different lines standing in parallel. These blue bars are pipelines, meaning registers. So every clock data is shifted from one to another. That means if in this position we have pixel I, then after a register we have the previous pixel I minus 1. And after another register we have I minus 2. And so in that case, what we see is that in the same clock, we have all the 9 pixels, the pixels clock, 1 pixel in the left, 1 pixel in the right, the 3 pixels on the upper line, and the pixels on the lower line. All of them are in the same time, so now we can do the multiplication in parallel, and then go and do the summation of all 9 solutions and send the data out. Obviously, we can add more pipelines in all kinds of places in order to improve the clock rate, but this is the basics of understanding that when doing the algorithms in the FPGA, it's vector processing, it's symbolic arrays, and we're just passing the data through an array and getting all computation in parallel. Moving to a higher level, then the data input and the data output, these two links can be linked to another algorithm, another pass directly, meaning we don't need to go to the DRAM and back from the DRAM, or to the cache and back to the cache in order to get from one element to another inside the algorithm or between the algorithms. So these are the internal direct connections. Because we have these direct connections, it reduces a lot of the power, and also because the processing is doing exactly the bits that are needed, it's also reducing the power. So what we can see is now measuring the performance. Not only that the processing is different in the FPGA and in the CPU, also the way of measuring the performance. In the CPU, normally you have an algorithm or a program or something, and you're asking how fast can it run on a certain computer. And then you look at the total algorithm that you want to run, sum them all, and then you know the performance that you need. In the FPGA, it is different. First of all, you get the performance that you want. That's not a question at all. If you want to have a gigapixel per second, you'll get a gigapixel. If you want to have 10 gigapixels per second, you'll get 10 gigapixels per second. You need to write the code accordingly, and you'll get it. What is measured is the resources that it takes. How much lookup table does it take? How much internal memories it takes? How much DSP blocks it takes, and so on. And then when you want to look how much the full resources that you need, you just add those sizes and resources, and then you know what FPGA can do the job. And if not, you can tailor several FPGAs in parallel one to another in order to get more performance. So what are the FPGA challenges? Well, what we can see is that within the FPGA, it enables really fast computation, low power, low cost, of course, when the code is optimized, and it is been used for more than 30 years, heavily in all kind of places where they did care about either the pricing or the power and so on. And even we at Gidel have worked on vision algorithms acceleration in FPGAs 30 years ago. So nothing about that is new. And the question is, if so, why the FPGA known use is so limited? And the answer is split into two major areas. One area is that people who are forced to use the FPGA in order to get what they want, in many cases cannot get off-the-shelf grabbers and off-the-shelf product to be able to do that. And therefore, these people are under the radar of the normal researchers of the machine vision market and so on. The second reason comes from many things. So first of all, it is harder to design and develop with the FPGA because the language is lower than the high languages available for software development. And basically, the speed up in the FPGA comes from the fact that all the lines that we write and all the logic inside the line, everything runs in parallel, and therefore it is harder to verify and understand what we are designing because the code on top and the code on bottom all happens at the same time. Then there's some specific issues such as clock crossing and so on that makes life harder in FPGA and do not exist at all in software. The other thing is that headcount. Simply, there are much less FPGA designers than there's GPU designers, and definitely less than CPU designers or software designers in general. And that's why also it is in many places hard to find these skilled engineers to do the job. From the FPGA perspective, it is long compilation times. In the imaging and machine vision, normally the compilation time for FPGAs is short. In many cases, it's less than an hour. However, for software engineers, an hour or half an hour compilation sounds ages. In full-blown FPGAs, sometimes compilations are half a day, and we've seen also more than a whole day of compilation time. And in order to answer also for a given answer for those who are forcing to build their own hardware all the time, they're doing that because of limited availability of a full flexible solution that are off the shelf and enabling the customer to build exactly what they want, either the external IOs that they want, the streaming data that they want, or just regular grabbers, but to enable them to get the full extent of their algorithms. So what drives now to use the FPGAs? I think this is a very, very interesting question. I've seen in the algo trading in the past, in 2007, people in the algo trading say there is no way that the FPGAs will penetrate and be used because of regulations and its banking and many aspects. Then they says, okay, how can we use FPGAs? And 5 years later, it looks like if anyone will not use FPGAs for algo trading, they will be out of the market just because a microsecond delay cost millions of dollars, and that's already 10 years ago. So sometimes changes in the environment and in the needs drives to use the FPGA much more than before, even though the FPGA have existed for many decades. And what happened now? Now we see really a very steep ramp in the sensor sizes, and at the same time higher frame rate, which enables to have pixel rate running at speeds that are way beyond even the 8K cameras and so on. And on top of that, there's a growing use of cameras in a system, new applications and innovations, and therefore the growing need for processing and compactization and power and so on are ramping steeply, and just cost effective. I can say that I've seen server rooms for imaging application that the server room cost about $500,000, and using FPGAs, it could have been reduced to less than 100K, and the power consumption can go to something like less than 5%. And obviously in the server room, the power consumption and getting all the power in was a big issue in some installations. So this is a kind of examples why we should need to move into that direction. So one thing is libraries. It's always good that there's libraries. The FPGA libraries name is normally called IPs, comes from intelligent process property. And that's because it's a lot of cells in IPs in the market. Then a high-level synthesis, meaning that you can write in C or something like that, and then compile into the FPGA. This is easier to use. However, normally it is limited with the complexity that can be done with it and with the efficiency in the FPGA. So in some cases, it can be used. In others, it's not good enough to have the full performance. Then hybrid computing. Normally, we are talking today more and more about hybrid computing. Then in that case, it's important to know that not everything should be optimized using the FPGAs, and not everything should be optimized not using the FPGAs. So combining the FPGAs together with the software can yield much better solutions. A good example for that would be a histogram. Running the number crunching to get the histogram table out of the image or out of the video, that is easily done in the FPGA and takes a lot of processing out from the CPU. On the other side, analyzing the histogram is a complex logic, and that is better to do in the software. It doesn't take a lot of processing power from the software and from the CPU. And then this is a kind of hybrid computing that really works well. In order to use hybrid computing, it is important to use virtual FPGAs that you can use, like drag and drop hybrid components, including the their portion in the DRAM, the portion in the FPGA, and the portion in the software, and you can look at them from software aspect as a single class and put them wherever you want. Then to accelerate the productivity, it's important to have a strong capability for debugging, testing, and system validation. Also, the ability of the virtual FPGAs enables to take a well-tested application, including FPGA part, and put it in a deployment. And this way, it reduces a lot of work and a lot of integration. And of course, it enables also to get much better reliability. And then in the hardware, you need some flexibility, different cost performance, and so on. So different solution enables customers to tailor the relevant cost performance according to their system needs. So we will move into a demo. The demo will take the hybrid computing and the virtualization element. So what we will see here is a debugging environment to develop a new algorithm that we want to run image processing in the FPGA. So the green part is the FPGA board that we are developing the algorithm in. The top part is the host computing, can run either debugging tools or user application as a C++ class or API or whatever to communicate with the user IP and close those as a single virtual element that can move from different boards and different needs. And even the whole blue part of the frame grabber and IPs flow can be portable between developing environment and frame grabber, and the frame grabber can be moved between different boards, different interfaces, and so on. So the same development can go into CoExpress, Tangivision, future IP interfaces, and so on. So how do we accelerate this debugging? So the first thing is we take off-the-shelf camera simulator solution. The camera simulator solution is already an application that has its GUI or API for further processing. It is using portion of the FPGA board, a portion of its DRAM. Even if it's only a single DRAM bank, it takes part of the DRAM bank, and it takes an IP to run this within the FPGA in order to generate the relevant data stream according to image processing pipeline. On the other hand, we have a frame grabber that is, again, have its own part in the software that has either GUI to be able to go and store or display, and it has an API to go to software applications. At the same way, it has the logic that enables that, and it has the DRAM portion of the frame grabber in order to send it out. In this demo, we will show an example of a grabber that enables to grab many cameras. In our case, we will grab just 2 cameras. One camera would be the original data that comes in. The second camera would take the images that comes after the processing, image processing, and therefore we would be able to verify immediately what we are doing and what we are achieving. So now let's go and see this demo. So the first thing is we have a debugging mode. In the debugging mode, we have access to the brightness element of the IP. So right now we're just doing a very simple IP, changing the brightness. Then we will move into the simulator. Over here, we're just having parameters of simulators. So we took a Bayer format, 8-bit per pixel, and we just took street things, and we just run the scenario over here. And here we have the vision application, and we can see this is moving. Currently, we selected 3 frames per second, so it would be easier to see in the video and uploading. And now if we go and change the brightness, for example, we would have a stronger brightness. Then, okay, we can see that the image below is brighter. Sorry. Okay, we can see the image below is brighter. And if we want to make it darker, we can go and make it darker. Okay, so this way, what we are able to see is that we can access immediately to the algorithm we're developing. We can take data, series of data through camera simulators, send it to the grabbers. And if we would like, we can go here and change. We can change just to take patterns like ramp patterns, and then I can start the patterns. And if we go over here, we can see exactly now we are running patterns, and we can go and run different scenarios. So this enables us immediately to run our testing on vast of different data and different parts. And that gives us a huge advantage compared to even developing algorithm in software, because when we're dealing with a huge amount of data, we want to test it also and to validate the system on a lot of information. And that's exactly what this kind of development environment enables us to do. So I would like to thank you very much for listening. I hope it helped you, and good luck with your projects.
Thank you so much, Ruben, for joining us to share your experience and highlight how FPGAs enable faster raster processing and lower power consumption. Before we wrap up here, to everyone in the audience, if you have any questions or comments, you can type them right into the conference chat box that is on your screen. And do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we hope you're enjoying the 3rd annual Vision Spectra Conference. Thank you all so much for joining us.